So typically when we're looking at a reaction mechanism, or if we're trying to figure out what the mechanism for an enzyme is, we have much more complex equations than simple first order or second order reactions. And so the math becomes very difficult to solve by doing integration. And so we can't do this analytically, and therefore we have to, in order to make simpler mathematical problems that we can solve, we have to make a lot of different assumptions. And so this is a typical mechanism that you might see, or a very simplified mechanism for an enzyme, where enzyme binds to substrate in the first step, in a reversible binding step to form the enzyme substrate complex, and then there's an irreversible step, chemistry step, where the substrate is both converted to product and the product is released simultaneously to regenerate the enzyme and then release product P. Now notice for the reversible step, you have two rate constants. You have a forward rate constant in this case, which I've denoted as K1, and then a reverse rate constant for dissociation of the substrate from the enzyme substrate complex, which I've denoted as K-1. In the second step of this reaction pathway, the enzyme substrate complex is irreversibly converted to enzyme and product. So there's no back arrow. There's only one rate constant here, and that's the forward rate constant for the conversion of the complex to E plus P, and that's denoted as K2. So in order to start solving the equation, we're going to start the way we normally start here, and then we're going to look at what do we have for initial concentrations, and what do they get converted to. So initial concentration of E, as time progresses, is going to be converted into a combination of enzyme substrate complex, and that's it. There are no other enzyme complexes that are in this mechanism. So we can say that the initial concentration of E at any given time t is going to be equal to the amount of enzyme that still doesn't have substrate bound plus the amount that has substrate bound at any time t. Okay, we do the same thing for S naught. We have free substrate, ST plus enzyme substrate complex at any given time t. Okay? Now, what we're going to look at was we're going to try to figure out what is the rate of P. So when we do this, we do what's called initial rate analysis. And so we define that as V, and we'll discuss this more later. But we're going to define V as the change in the product P, so the formation of the product P over time. Now that's going to be equal, that's going to be, the only way P can be formed is by formation of the enzyme substrate complex. There are none of these rate constants relate directly to formation of P, and so we set this equal to K2 times the concentration of ES at any given time t. Okay? And so remember that this is formation of P, so this is positive, this is not negative, and so this is how we set up the equation for this. So now we have to figure out how do we know what the concentration of enzyme substrate complex is at any given time. So in order to do that, we set up DES dt, and then we look at what is forming ES and what is consuming ES, which of these reactions. So formation of ES only occurs from K1, and so that's the only positive we have here. So K1 times enzyme times the substrate. Again, those are E of T and ST. Now we have two reactions that consume ES. So one goes back to substrate dissociation to form enzyme and substrate. So this is dependent on the concentration of ES. Minus K-1 ES T. And then we have a second consumption pathway where ES is being consumed to form enzyme and product. That's irreversible. K2 ES T. All right. So now we have all the rate constants and then their relationship to different concentrations of species along the pathway as it relates to the change in ES over time for any time. So now we have to solve this. Now this is where the problem comes in, because if we're trying to solve this the same way we did before by integration, we're going to have a difficult time here. So we make a couple of assumptions to make our life simple. The first one we've already seen before, and that's we do this in pseudo first order conditions. And so in our pseudo first order conditions, we're going to do the initial substrate concentration is much greater than the initial enzyme concentration. So that means that the change in the substrate concentration versus time is negligible. So these are going to be effectively equal to 0, and that's going to cross out. The second assumption we make is called the steady state approximation, and that's where we set dEs over dt equal to 0. Like so. That you may not be able to see. Okay, so we're going to set this change in the ES over time equal to 0. So the idea behind that is what we're saying is as soon as enzyme substrate complex is being made, the rate for the consumption of it is equal to that rate of the formation. That's not necessarily a correct assumption to make, but again, it helps to make the math easier. So what this does is this sets this entire equation equal to 0, and after some substitution, so the first thing we have to substitute is we have to substitute in for E of t and also for S of t. So remember, this just gets always substituting for S of t as S naught. We rearrange this equation for E of t, and that gives us E naught minus ES of t times S naught, again, something that we control. S naught is experimentally controlled, minus K minus 1 ES T minus K2 ES T. That looks like that's getting smaller. Okay. All right. And then what we get when we multiply this all out is K1 S naught U naught minus K1 S naught ES T minus K minus 1 ES T minus K2 crab walk. All right, so notice then that every term, and this is all going to be equal to 0. Notice that every term that has EST in it also is negative. All right, so if you're deriving this, you should check for this, because if it's not, then it's not done correctly. Okay, so what we're going to do now is we're going to rearrange this so that all of the ES terms are on one side of the equation and all of the non-ES terms are on the other side of the equation.